In this example, I'm going to introduce you to some of the drawing tools built into DirectMath software. The drawing tools in DirectMath, first of all, contain a set of standard drawing elements that you've come to expect from most common drawing programs. These standard elements allow you to create and manipulate simple shapes in a drawing. In addition to these elements, DirectMath also adds some elements which are useful for making mathematical drawings. One of these is the ability to add a plot to a drawing, and as you can see, I've done this already in this example. In this example, we're going to be working with this curve that I've already illustrated via a plot. Now, in addition to the standard tools and the plot tool, the other tools that are available here are all tools for creating and manipulating constraints, and it's these constraints that give the drawing tools in DirectMath their particular power. In this example, I'm going to be taking you through a demonstration of Newton's method, which is a standard method in calculus used to approximate roots of curves. The first step is to create a line which is an approximate tangent line to the curve in question. Right, we do this by simply sketching in a line, and one more thing we'll need to make our tangent line is we'll need a point of attachment. We do that by creating a vertex and then dragging the vertex over to the point where it sits on the curve. Right, then we click to select, make sure that all three elements, the curve, the line, and the attachment point are all selected, and then we can come down here and click the button to attach a tangency constraint to these three elements. Now, once that constraint has been attached, this line segment is now constrained to be tangent to the curve, which means that as I click and drag to reposition the line segment, the system built into DirectMath will try to maintain that tangency constraint. And of course it does that primarily by moving the point of attachment around as I click and drag to move the curve. Now, the next thing we're going to be interested in here is the point at which this tangent line crosses the axis. Now, to study that point, I'm going to create another vertex, and I'm going to place that vertex close to the point where the tangent line crosses the axis. Now, because I want to have more control over exactly where this vertex is located, I'm going to attach a vertex constraint to it. Now, simply clicking the vertex constraint simply fixes the point in place so we can't move it. To make this a little bit more useful, I'm also going to go in and attach a label to the constraint. What the label allows me to do is it allows me to basically specify where this point will be. And I'm going to do that by simply editing the label so it forces the point to lie at a particular point in the drawing. In this case, I want to constrain this point so that its x-coordinate is x1 and its y-coordinate is 0. Now, once I'm done finishing editing that constraint, I have to go up to the drawing menu and choose the option to do what's called validating that label. That basically makes the constraint live, so this is now active in the constraint satisfaction system. Now, as you can see, as I click and drag to move this point around, the constraint specifies that at all points in time the y value of this point should stay 0, which is why the point is staying on the axis even as I drag it around, and at the moment the x-coordinate is unconstrained. Right, now, the next thing I'd like to do is I would like to attach that point to this tangent line, and we can do that simply by clicking and making sure that both the tangent line and the point are selected. And once they're both selected, I can go up to this pane and drag to make an attachment between these two things. So now the point is attached to the line segment, and whenever I move the line segment around, the point will stay attached to it. Now, the next step in Newton's method is to study a point which is on the curve directly over this crossing point that we have just established. Right? So to do this, I'm going to create another vertex in my drawing, and I'm going to drag that vertex down so that it's somewhere below the first point. And once again, we'll attach a constraint to that vertex, and we'll attach a label to the constraint that will give us more control over precisely where this point is located. Now, in this case, what I would like to do is I would like to specify that this new point has the same x-coordinate as the first point, and I would like to simply say that its y-coordinate is a value y1, which we're going to specify in a minute. Right, so once again we go and we validate labels, which then updates the constraint on this point. Right, now the second point is now constrained to have the same x-coordinate as the first point, and at the moment its y-coordinate is unconstrained, so I can drag it around and move it anywhere I like. All right, so what I'm going to do next is I'm going to position that point so that it sits on the curve. Now the next step in Newton's method is to create a second tangent line. So to do that I'm going to come in and sketch a second line, which is an approximate tangent at this second point, and we'll drag that over and position it over the point that I just established. Right, and then once again I click to select all three elements, and with all three of those elements selected I can then create another tangency constraint at this second point. Right, now once that tangency constraint is live, I can click and drag to move any portion of the drawing that I like, and the constraints are maintained at all times. In particular, the second curve is constrained to be tangent to the curve, and as I click and drag to move things, everything gets updated automatically. Right? And as the example here illustrates, what Newton's method does fairly effectively is, after a couple of iterations of constructing tangent lines and watching where these tangent lines cross the axis, we see that this method converges fairly rapidly to the actual root of the function in question.